Alright, so here we're going to be solving right triangles. Uh, Previously, we've put the sine and theta in terms of a unit circle or some circle that had a radius not of unit length, right? We called it r. Here we're going to take the sine and the cosine completely outside of our coordinate system and simply look at right triangles, right, in space, right? So our theorem here, so we're going to introduce the theorem, and then we're going to look at some examples applying this theorem. So suppose theta is an acute angle residing in a right triangle. If the length of the side opposite theta is b, the length adjacent to theta is a, and the length of the hypotenuse is c, then cosine theta is equal to a over c, and sine of theta is equal to b over c. Okay, so no point in the coordinate system, we're simply looking at triangle and their lengths. So I'm going to use this theorem to solve this problem down here. Okay, so it says example, find the measure of the missing angle and the lengths of the missing sides. All right, so we know two triangles here, right? It's a right triangle. And again, remember, this formulation, as the theorem states, only works for right triangles. If we do not have a right triangle, this does not apply, and we need other methods to solve for the missing lengths and sides. Okay, now, according to this theorem, if we treat this as our theta, the side adjacent is A, the side opposite is B. Again, hypotenuse always across the right angle, so that would be C. Okay, and then also understanding that the sum of the angles is 180. If this is 90, this is 30. That means this is 60 degrees. Okay, so that we were able to find without using that theorem. But to find the A, B, and C, hold on a second. I believe I missed. We need one other piece of information here. Yeah. Okay. This is given to us. A is 7. Okay. All right. Yeah, without that, we wouldn't be able to get far. Okay, so let's say we're given 7 and then the angle of 30 degrees. All right, so now we can apply this theorem here where we have, okay, let's apply it to find, let's say, B, right, opposite here. Or, excuse me, let's use it to find C first. So cosine of theta would be equal to A over C. And then I'm going to plug in the values that I do know. I know theta is 30 degrees. A is 7. And C is unknown. All right. Okay. So cosine 30 degrees, all right, or pi over 6. Take out my trusty unit circle. I have a copy of it. If not, I memorized cosine of 30 degrees, and I know that to be root 3 over 2 is equal to 7 over C. All right, and then I'll just solve for C here, right? So we can do this a couple different ways here. I'm going to take the approach where I multiply both sides by C, right, to get the C in the numerator, which is what I want, not in the denominator. So we get C root 3 over 2 is equal to 7. And then we multiply by the reciprocal here, both sides, 2 over root 3, 2 over root 3. And this reduces to 1, so we're left with C equal to, remember this is 7 over 1, right? Watch our fraction multiplication. 7 times 2 is 14, so we get 14 over root 5. Okay. All right, so that gives us our value of C. 14 over root 5. All right, so now last thing to find is the value of b. All right, so b, there we'll use, it's the opposite, so we're going to use the sine. Let me write it over on this side now. Let's move over here. And we have sine of theta is equal to b over c. All right, let's plug in what we know. Sine of 30 degrees equals to, b is unknown, and c I found already, right? It's 14 over root 5. All right, or I can write this as sine of 30 degrees. I want to get rid of this complex fraction. I don't like this, right? I don't like when there's a fraction over a fraction. So that reduces to, or simplifies to, b root 5 over 14. Okay, much better. All right, so now again, let's take a look here from our unit circle. All right, look it up, or from memory. Sine of 30 is 1/2. Okay, and then here, b 5 over 14. Okay, solving for b, I'll multiply by the reciprocal here, 14 over root 5. 14 over root 5. All right, so that reduces to 1. And here we have b. On this side, I can reduce this. We get 7 over root 5. Okay, now let's do one more example here. Okay, where we use this theorem here. Okay, so here we're asked to find alpha, a, and b. Now in this case, we're given the hypotenuse, right? So this is our c. The hypotenuse, again, how do I know it's a hypotenuse? It's the one opposite the right angle. Okay, and we're given sine of 33 degrees. Okay. Okay, so here we'll do sine, and then we'll call this our theta. Sine theta, and the sine theta again is always the opposite, so b over 8, or b over c. Then I'll plug in everything I know. Sine of 33 degrees is equal to b over 8. And then times 8 on both sides. That reduces to 1, and we get b is equal to sine of 33 degrees times 8. Now, when we have an angle that is not on our unit circle, then we'll use our calculator to calculate the value here. All right, so I expect that if it is an angle that is 45 degrees, 30 degrees, 60 degrees, or some multiple of that, right? I would expect that you give me an exact answer, all right? But here, since it is not one of those angles, I'll use a approximation, right? Excuse me. First thing I want to make sure is that I am in degrees and not radians, which I am. So we'll do sine of 33, close parentheses, times 8. And we get 4.36, we'll call it, rounding to 2 decimal places. Okay, now in a similar way, I'm going to use the cosine of theta. So cosine theta is going to be equal to a over c. All right, plugging in the values that I know, we get cosine of 33 degrees is equal to a over 8. Multiplying both sides by 8, we get A is equal to 8 times cosine of 33 degrees. And again, not a common angle that's on the unit circle, so I will have 8 times cosine of 33. And that is approximately 6.71. Okay, and then the last part, alpha. Alpha is 180 degrees, which is the total number of degrees in a triangle, minus 33 degrees, the given angle, and the right angle. So that gives me 180 minus 33 minus 90, 57 degrees. Okay, and now we've solved the triangle, right? We know all the sides and all the angles. Okay, thank you.